Hello, Past Paper Guy here. What we're going to be doing today is we're going to be solving the EDUQAS June 2019 Electronics Component 1 GCSE paper. I've put a link in the description of how you can find this paper. It's all freely available on the EDUQAS website. So without further ado, we'll go through the solutions. It's an easy logic question to get you started. Label pin 6 on the chip, so you always start at the blob here and you go counterclockwise like this. So 1, 2, 3, 4, 5, 6, that is pin 6. How many logic gates are on here? There are 4. How many inputs does each one have? Has 2 each. Name the type of logic gate. That is an AND gate. For each of the following truth tables, name the logic gate and draw the symbol for the logic gate named. So this here is, if this was 0, 0, 0, 1, it would be an AND, so this is a NAND gate. And the symbol for the logic gate there looks something like that. Looks like that with a circle in the end. And this one here is an OR gate, and the symbol for an OR gate looks like that. Question 2. So we've got sensing units, signal systems and output systems, and we've got to sort these into these categories. So pretty straightforward, this one. A delay unit, they say, is a signal process. It takes an input, delays it. A motor unit's an output. An OR gate is again a process, got inputs and outputs. Temperature sensing unit, well, that's a sensor, so it goes here. And then the comparator is a process comparing two things. Part B. A large house in the country has a long path leading to the front door. A system is required to turn on a set of LED lights to illuminate the path and the visitors. The lighting system should only operate if it's dark, so we're going to need to use a light sensor. The lighting system should be operated either at the front door or when someone opens the gate, and the LED should remain on for a fixed period of 3 minutes and then switch off automatically. Okay, so the thyristor here is a red herring because that's no longer on the specification. So we just need to put these things into here. So it can only work during the dark. So if we put a light sensor here, and we want this and this situation up here, so we want an AND gate here. Right, this one's always easy to do. Whenever you have an output like LED lights, the thing you need before it is you need a driver. So we're looking for a transducer driver. There we go, transistor driver, this one. So if there was a MOSFET driver there, you could use that as well, but that's not there. Okay, and then we have the house switch, and there's another switch as well. The gate, I think, is the other one. There we go, front door or the gate. So that's the house, and then we want the gate. So we want a switch unit for the gate there. And either of these, either or this, will make it work. So we want an OR gate here. Next one, using the axes provided, sketch the output signal required from the delay unit. So we want it to be 0 until the trigger is applied here. It goes to a logical high there, and then it delays for 3 minutes. So 1, 2, 3, it goes to 4. Don't put that at 3. And then that down like that. and along like that. Question 3, we've been given 3 circuits and we have to work out which one of these will be the brightest. So to understand that, we need to understand that the lamp will be the brightest because they've all got the same potential when this resistance is the smallest. So here we've got 20 ohms, here we've got 5 ohms because they're in parallel, and here we've got 5 plus 10 is 15. So it will be this one as the resistance is lowest. So that is B. Right, draw a labelled network of 2 resistors that will produce a combined resistance of exactly 12 kilo ohms in the space below. Following resistor values are available. Okay, so we're only allowed to use 2, and we're only allowed to use each one once. Right. Well, to do a question like this is usually a little bit of trial and error, trying to figure some things out. So we can do a little bit of process of elimination. We can't do anything in series because if we added 2 of these together, we would already be over our 12,000 ohms. So we need to put 2 into parallel. Now the rule of parallel is that the resistance of resistors in parallel is always smaller than the smallest of those resistors. So we can't have the 10k in parallel, that's ruled out. So the next thing to do is to try these 2. So we've got an 18k there and a 36k there. Now there are multiple ways you can work this out. The easiest is probably to do the product over the sum. So if we do 18,000 times by 36,000 and we divide that by 18,000 plus 36,000, lo and behold, we get 12,000. You could also have used the full 1 over R1 plus 1 over R2 equals 1 over R total. I'll just do that for you quickly. So we can get rid of the thousands if you want. So we can do 1 over 18 plus 1 over 36 is equal to 1 over RT. So if I put in 1 divided by 18 plus 1 divided by 36, that's 1 over 12. We have to flip the thing upside down, so we get RT is equal to 12. And remember, I did this in kilo ohms as my unit, so that would come straight out in kilo ohms. These ones, there's always a question that's like this in every paper. The configuration will be different, but the rules are the same. It's just Kirchhoff's laws. So here we've got 10 amps coming in here, we've got some coming out here, we've got here we've got 10 milliamps coming in here, we've got 2 milliamps coming off here, so how much goes off there? Well, they have to add up to the 10 that was going in, so that's got to be 8 milliamps. I2 is this one here, well 2 and 8 join back up to make 10 milliamps. It's actually what we started with here because both of those split and then join back together. And then V1, well that voltage plus that voltage must be that. You start at 0, we go up by 2, up by 4 to get to 6, so that's got to be 2 volts. V1 plus 4 must equal 6. Calculate the value of R. R is equal to V divided by I, which is equal to the potential across it, which is 4, divided by I, which is 2 times 10 to the minus 3. Put that in your calculator and you get 2,000 ohms. It's equal to 2 over 10 to the minus 3, which is 2 times 10 to the 3. Another color code with resistor has white, brown, red, gold. What is the value of the resistance? Well, for that you need to either know this or look it up. So white is 9, brown is a 1, red is 2, so that means you add 2 zeros, and we put the ohms on. Gold is plus or minus 5%. A comparator is used in the system to warn a driver when the temperature outside the vehicle is just above freezing. So you need to know the name of a component that can be used as a sensor. Well, the one that you know is a thermistor. Don't try and be smart and write something off syllabus like a thermocouple. Just stick on syllabus. Part of the circuit is shown below. The LED should light when the temperature falls below freezing. So the sensor is going to be connected to the non-inverting terminal of the op-amp, which means that when this value is bigger than this will saturate positively, which will turn the LED on. So here we need this to be big when we want it to be on, which is when it's cold. Now, if you remember, the resistance of a thermistor looks like that. So it's going to have a big resistance when it's cold. So that means we want it at the bottom of the sensor, of the potential divider there. So now when it's cold, this will be big, this will be small. So this value will be closer to this value than it is to this one. So it will light the LED there. Explain the purpose of the variable resistor in the circuit. Well, if we have this variable resistor, we'll be able to change V minus. And if we can change V minus, then that allows us to change the temperature at which it flips. So remember always to link it to the point of the circuit. So, so to change V minus in order to adjust the temperature at which it changes. Determine the power dissipated in the 330 ohm resistor when the LED has a current of 30 milliamps flowing through it. I'd strongly recommend you write on. So we're going to need P is equal to I squared R is going to be the easiest. We could work out the voltage across the resistor there, but that's just one extra step. So 30 times 10 to the minus 3, we need to square that, and then we need to times that by 330. Right, so you need to get your calculator to do this bit here. So we have 30 times 10 to use this button for times 10 to the power minus 3, and we want to square that. So we get, that's that bracket there, and we times by 330, press this, press that. So this button here changes it into standard engineering notation. So that's 297 times 10 to the minus 3 is milli, and the unit of power is watts. Part D. Comparator has a saturation values of 12 volts and 0 volts. Calculate the voltage drop across the 330 ohm resistor when the current through it is 30 milliamps. So we're going to have to do this anyway. So we're going to do V is equal to I times by R, which is equal to 30 times 10 to the minus 3, that's the current, times by 330. Now if you'd done this a slightly less useful way, you could have worked this out before. So we do 30 times 10 to the minus 3, and then we times that by 330, and we get 9.9 volts. So we've got 12 volts here, we've got 9.9 volts there. So what's the resulting voltage drop across the LED? Well, we've got 12, 9.9 goes across there. So 12 take away 9.9 gives us 2.1. Because they've got to add up to 12. Right, we've got some LEDs that we can choose here. Which one will we pick? Well, or which one have they picked? So it's a bit of deduction. So remember this is the maximum current. So 30 milliamps is less than all of those, so that's fine. The wavelength is just corresponds to the color. So we need to pick the one with the correct voltage. So we've got 2.1 volts, so it's that one. So it's the yellow. Right. Question 5, we've got a logic system here. We need to do some Boolean expressions. So for output X, well, X is not C. So we put C Like, remember it says in A terms of A, B and C, so we can't use output X in later. Output Y, this is a NOR gate, so that is using the inputs A, NOR B. You can also write that as that. Both of those are equivalent. And the output Q, it's X or Y, so it's not C or A or B, like that. That's the same also as not C or A dot B, both of them knotted like that. Complete the following truth table. So let's work out X first. X is not C, so it's the opposite of this line here. So it's 1, 1, 1, 1, 0, 0, 0, 0. Y is A nor B, so it's high when they're both low, otherwise it's 0. And Q is this one or this one, which is 1, 2, 3, those ones. This one makes it high, and these are therefore zeros because it's this line or this line. Redraw the logic gates with NAND gates only. Right, so you need to know your NAND equivalents here, but you can work them out on the spot. So C is going to be a NOT gate, which is that. The NOR gate here is, well, if we think about it in terms of Boolean, we've got that, and we can always double invert things, so we can do that. So we need A, so that's that bit, B, so that's that bit. We NAND those two together, so that's that bit, and we've still got this line here, so we need another NOT gate in there, like so. And then this one is an OR gate, so X or Y. If I put a double inversion on that and then apply De Morgan's theorem to that, we get this. So we need to knot the two inputs and then NAND them together. So this is now X, this is now Y, and we need the OR gate rule here. So it's just like the NOR gate, but without the last NOT on there. Now, one way to do this is just to learn all of these off by heart. Right, cross out any gates that are redundant on the diagram. So always group them together when you're doing this. So you need to find ones where you've got a NOT gate following another NOT gate directly. So you've got that there, and you've got that pair there. Question 6. So we've got a circuit with a transistor driver. We're driving a motor. It's got a protective diode. The diode is, of course, protecting the transistor, not the motor, when the motor turns off. Right, the motor operates at 9 volts, 500 milliamps. Calculate the power dissipated when the motor is operating at these values. So P is equal to I times by V. So the current is 500 times 10 to the minus 3 times by the voltage, which is 9 volts. Put that in a calculator. You can do this one in your head, but because that's just a half. But 500 times 10 to the minus 3 times by 9 is 4.5. So it's 4.5. And the unit is watts. Same as 4,500 milliwatts, just those two numbers added and multiplied together. The transistor has a current gain, HFE, of 200. The transistor has just saturated. Calculate the base current. Well, if there's 500 milliamps going down there, then we know that the base current, IB, times by the gain, HFE, is equal to the collector current, which is 500, and the units here are going to be milliamps. So sorry, I'll just put in collector current there, IC. So then we substitute in our values. IB times by 200 is equal to 500. So 500 divided by 200 is equal to 2.5. And I've got that in milliamps, so this will be milliamps as well. So 2.5 milliamps. The voltage across the 1.2k resistor, so this is 2.5 milliamps. So V is equal to I times by R. So we've got 2.5 times 10 to the minus 3 times by 1200, which is 1200 times by 2.5 times 10 to the minus 3 is 3 volts. So the value of Vn, right, so we start here at 0 volts. The transistor is saturated, it's on, so that means there's a voltage drop across this. This is like a diode drop, an NP junction, so this will be 0.7 volts. There's 3 volts across here, which means that we've got 0 plus 0.7 plus 3 volts. So this point here will be 3.7 volts. Got to remember to add in the base voltage there. Question 7. So this is the QER question here. So we need to not only get all the points, but also explain ourselves in a logical way in order to get all of the marks on this question. So we have the red valve, the blue valve, and the yellow valve called 1, 2, and 3. And each second that they're open, they dispense 1 milliliter of paint. 1 second delay is required between the closing and opening of a valve. To make a specific color, we need each of these pigments: 20 milliliters of red, 40 milliliters of yellow, and 50 milliliters of blue. So that's 20 seconds of red, 40 seconds of yellow, and 50 seconds of the blue valve being open. So the apprentice has written the following program. No doubt it will not work, to dispense the colored pigments. And we're going to evaluate it against the specification, clearly explain how the program agrees with or does not agree with the original specification. Right, now the big mistake that people make is they forget this bit, how the program agrees. Everybody always points out the mistakes, but what they don't point out is the bits that go right. So let's work our way through it. So the first thing I did when I did this was I translated these letters for R, B and Y onto this, because it was a bit confusing having the 1, 2 and 3. So valve 2 and 3 is the blue valve and the yellow valve. That's the blue and the yellow. Valve 2 is the blue valve and valve 3 is the yellow valve. So it opens all 3, waits 20 seconds, which means it's delivering 20 milliliters of, and notice these are in a different order to these, so just be careful. I'll write it in this order here. Right, so we're going to have 20 milliliters of that, 20 milliliters of that, and 20 milliliters of that one. Then we close them here. Then we're going to open the blue and the yellow, and we're going to deliver 20 milliliters of that one, 20 milliliters to that one, which gives us a total of 40 of that one and 40 of that one. So far we've done the red correct, the yellow is now correct, and the blue needs 10 more. We close the valves, we wait 1 second, we open the blue, that's correct, so that's going to be R, B, Y, so we're going to wait 20 seconds, oh dear, so we've got an extra 20 milliliters in there, which is going to give a total of 60 milliliters, and then we close the wrong valve, so then we close valve Y. Okay, so how are you going to organize this? There's multiple ways you could do this. You could answer the question by color, or you could just go through logically in order. I think this time I'm going to go through in order. So the program starts by opening all 3 valves and delivering 20 milliliters of each paint to the tin. Now, notice that I'm talking about paint. I'm not talking about waiting 20 seconds. Okay, so always relate, whenever you get a program, always relate it to the real world situation that the program is trying to affect. Okay, it then closes the valve, or closes all 3 valves. So the red now has 20 milliliters, which is to spec. It then waits 1 second, and that is what it's meant to do, which here it says, here it requires between closing and opening valves as correctly as per specification. Right, so we're now here in the bit. So now it opens the yellow and blue valves. Notice I haven't said 2 and 3. I've related it to the paints, and delivers 20 milliliters more of those and closes them. So now, which one has 40 milliliters? Now yellow has 40 milliliters. It waits 1 second again here. And that's correct. And then it opens the blue valve. To deliver the remaining paint. The problem is, though, that it delivers 20 milliliters instead of 10. And then it closes the wrong valve. Right, it doesn't in this one say how, sorry, it closes the wrong valve, it closes the yellow valve instead of the blue one. Now, it doesn't say here that you're supposed to suggest the fixes, but we'll write the fixes down anyway, why not? So what I would do at this stage is I would just mark on here a couple of points, so 1 and 2 fixes. 1, change wait 20 seconds to wait 10 seconds, and point 2, so these are C diagram or C flowchart, and 2 we need to close valve 3 goes to close valve. We want to close the blue one, which is valve 2 there. So that is one solution for this. You could have organised it by just doing the red paint first, then talked about the red paint, then talked about the blue paint, and talked about the yellow paint separately if you'd wanted to. It doesn't matter. What matters is that you have a sort of logical way that you approach the question. Now notice I haven't written in bullet points, but basically I have. If we'd put bullet points here, like so, then my answer is in bullet points. So you can just do that without writing the bullet points. In fact, EDUQAS don't penalise you for writing in bullet points on these questions like you might get penalised in other subjects. So you can write in bullet points if you want. Or you could draw a table here and present your answer as a table. What's important is that it's clear and easy to understand. If it's not easy to understand, then you won't get the full marks, even if you hit all of the relevant points. Okay. Question 8. Here we have a sensor unit. We've got a variable resistor and an LDR, 15 volts here, and V out here. So what is the resistance of the LDR at 200 lux? You need to get your ruler and you need to find 200 lux on here, which is there, and go up there and across. There. So I've got it at 245, and then don't forget the unit, kilo ohms. The variable resistor is set to 62.5K. Calculate V out at 200 lux. So this is potential divider equation. So V out is equal to V in times by R2 divided by R1 plus R2. And it's all quite straightforward, there's no rearranging here. The bottom resistor is this one. The R1 is this one here, which is that value. And then we need to put this one in again. Didn't put the times the line. So obviously the kilo ohms all cancel, and we can do 245 divided by 245 plus 62.5. Notice I put that in brackets, otherwise it won't calculate it for you properly. So that's the percentage, times that by 15 to get the value of V out. So V out is equal to 11.9512 ... So that's 12 volts to two significant figures. What happens to V out when the light level increases? Well, when the light level increases, the resistance is going to decrease, so V out will drop. Now, you don't have to explain that, because it just says what happens, it doesn't say to explain. Part C. The light sensor is now connected to a MOSFET. When the light level drops to 200 lux, a lamp is switched on. The lamp draws a current of 6 amps. Determine the minimum value of GM for the MOSFET. So we need to use the MOSFET equation. IDS is equal to GM times by VGS minus 3. Okay, and we're going to be rearranging for GM. So let's just put the numbers in first. It's probably the easiest. So IDS is 6. Is equal to GM. VGS is going to be the value that we calculated here, which is that value there, so that's 12. Take away 3, so that's 9. So GM is equal to 6 divided by 9, which is 0.67, and the units are the Siemens, so that's a capital S, like so. Complete the circuit diagram to show the final design of the lighting system. So we need to just add the MOSFET, that's all. Now we don't need a base resistor, because MOSFETs don't need base resistors, because they don't, no current enters the gate there. We need to put the light in here, which they like this symbol here for that one. Join that there, join that there. And that's that. That's the end of the paper.